So now we want to have some applications of the chain rule. So we have here the surface area in square meters of the human body can be approximated using the equation S, which is surface area, equals 1 over 60 the square root of HW, where H is height in centimeters and W is weight in kilograms. Well, technically that's mass, not weight. Weight is force, but that's all right. We'll just weight slash mass. All right, a child is 125 centimeters tall and has a mass of 34 kilograms. His current growth rate is 3 centimeters per year with a weight gain of 2 kilograms per year, or mass gain. Find the rate of change in surface area. Okay, so let's see here. If I was going to rewrite S, because I know I'm going to have to take a derivative of this, I'm going to rewrite it as 1 over 60 h times w to the 1/2 power. Because we've learned a long time ago that square roots and derivatives do not mix well. Now that S, that surface area, is based on h and w, right? So dependent on. Now each of those is dependent on time. You can tell because there's the weight gain per year. So height is dependent on time and weight slash mass is dependent upon time. All right, now we can use the chain rule. So the derivative of the surface area with respect to time, which is what they're asking us to find because they want us to find the rate of change in the surface area, which means we're looking for the derivative. Right, derivative is rate of change. We learned that in Calc 1. Okay, so we're going to have to break this down into some pieces here. All right, so if I look at this side of it, right, from my tree diagram, my chain rule tree diagram, the derivative of S with respect to t, and it is correct to use d's here because t is my only input variable when all is said and done, is the derivative of S with respect to h times dh dt plus, and then the other side of the house goes this way, which is the derivative of S with respect to w times dw dt. All right, and I can tell t is my variable because, of course, it's per year. All right, so now get to some fun stuff. We're going to have to actually find this. So that means that ds dt is equal to, and I'm giving myself some more space because I know how this is going to go. So I'm going to take the derivative of this with respect to h. So h is my variable, and I'm taking a partial derivative, of course, because there's two variables in there. So it's 1 over 60, and then take the derivative of that piece, which is a half h times w to the negative 1/2 times the derivative of the inside. Well, if h is your only variable, w is treated like a constant, like 5. And so you would say w. And then you have your dh dt just sitting right there. It just comes down. And then you'd add to it, and you basically do the same thing with the other side. So it's 1 over 60 times a half times hw to the negative 1/2 times h, right? And then bring the dw dt down. That comes right down there. All right, now that's actually the rate of change. I mean, we found it. I mean, we could simplify it a little bit, but it's not necessary because they didn't ask us to. But what they did ask us to do was to find the rate of change in surface area, and they're talking about this child. So it's sort of implied for this child. So I'm just going to say for this child right here. Because the rate of change of the surface area is right here. It's this big formula I just came up with. But if I want the rate of change for this particular child, then I'm going to substitute in all the values I know. Well, first of all, 1 over 60 times 2 is 1 over 120. Let's just be real about that. And then we want to take h and w. Well, this child is 125 centimeters tall, so there's the h. And then, let's see here, 34, so there's the w right there, right? So it's 125, and that's w, times 34, times another 34, because there's another w, and then dh dt, they gave us that as well, because dh dt is right here. There's dh dt. It's how fast they're growing. So this becomes 3. Okay. Then you add to it, and you do it all over again. So 1 over 120 times, let's see, 125, that's the height, 34, that's the mass, weight, and then h right here, which would be, let's see, that h is 125. And then dw dt was also given to us, it's right here. So dw dt is 2. So this will become 2. Now it's a little bit strange because when you look at this, it says the surface area in square meters of the human body can be approximated. So it says square meters and then it has centimeters in the formula, which is kind of interesting. So that means that when we come up with this answer, it's going to be in meters squared because they told us so. Meters squared right there. All right, now we are just going to go put this into Maple, right? So that is what it is for, or a calculator, you know, whatever makes you happy. And I actually did this in Maple, you can see. One second. I kind of played around with it. So I took the surface area function, I called it S5. Then I found pieces of it. I took the derivative in a slightly different way to do the chain rule. And I actually did it for the child right off the bat. So I said 3 and 2 right in there. And then I did a substitution where the height was 125 and the weight was 34. And you get this awful thing. So then I did it at 4 digits, which is 0.044996. And it tells us it's square meters. So you have to pay attention to the formula. I mean, if the formula says it's square meters, then you have to believe them. So that gives us our answer. So our answer through Maple is 0.044996 meters squared per year. And there we have it. Now, if you wanted it in centimeters squared, you know, just for fun, what you'd have to do is you'd have to multiply by a fraction that makes the meters go away and the centimeters gets introduced. But of course, you'd have to do it twice because meters is squared. This 1,000 would move the decimal 3 spots over, and the other 1,000 would move it 3 spots more, so that'd be 44,996 centimeters squared per year. Either one is fine. All right, so that was a pretty straightforward application, not too difficult. Now we're going to learn another application, which is very useful because it gets us out of having to do some work from Calculus 1, which we love. Now, we learned how to do implicit differentiation in Calculus 1. So we began with an equation that contained variables x and y, but is not solved explicitly for y. I mean, because when it's solved explicitly for y, that's easy. But then we would have equations, say like this one right down here, where it would have x's and y's mixed together. And so we would have a process for finding the derivative dy dx from this. All right, so let's do that, shall we? Let's practice some Calculus 1. So you take your equation, x cubed plus 3xy squared minus y to the 5th equals 0. And what you do is you take the derivative of both sides with respect to x. So you say, all right, I'm going to take d over dx of this whole thing. This is an operator, right? I shouldn't put a dot there. It's not multiplied. You're taking the derivative with respect to x of every piece of this. Okay, so let's look at the first part. If you take the derivative of x cubed with respect to x, that's really easy. It's 3x squared. And then you were taking dx with respect to dx. I mean, we usually don't even show this part because, of course, dx over dx goes away and is just 1. But nevertheless, you have it. All right, now this middle one, there's a multiplication there, so we're going to need product rule, everybody's favorite. All right, so let's take the derivative of the x part, which is just, well, the derivative of the 3x part, which is just 3. So you'll say 3, and then leave the y squared alone. And of course, you were taking the derivative of the x part, so that's times dx over dx, which again, we usually don't even bother showing past the first time we learned this in Calculus 1, but I thought it might be helpful to us right now to kind of remind ourselves. And then now leave the 3x alone and take the derivative of y squared, but with respect to x. So that's times 2y, but y is a function of x. That's the part you don't want to lose sight of. right? Y is really a function of x. So when you take this derivative, you have to multiply by dy dx. And then now there's a minus, so minus, and the derivative of this last one is 5y to the fourth, but again, the variables don't match. Y is a function of x, so we'll say dy dx. Now what we're trying to solve for are these two pieces, right? The dy dx pieces. So we need to get them together, and we need to get anything that doesn't have a dy dx in it to the other side. We're basically doing algebra, right? Glorified algebra. All right, so over here we have a 6xy dy dx minus a 5y to the fourth dy dx equals, and I'm going to bring these two to the other side. So it's going to become minus 3x squared. I'm just going to write it. Minus 3x squared minus 3y squared. Right? These two are going to be subtracted and removed. All right. So again, here are the pieces I want. And there's two of them. That's not good. I want one. So I'm going to factor it out. So I'm going to factor dy dx out. And that'll leave me a 6xy in the first term minus a 5y to the fourth in the second term. Now to get dy dx by itself, I divide everything by that denominator. So dy dx is equal to negative 3x squared minus 3y squared over 6xy minus 5y to the fourth. Now, I could factor a negative out of the numerator and denominator if I so desire. If I factor a negative out and factor a negative out, it will turn it to 3x squared plus 3y squared divided by negative 6xy plus 5y to the fourth. It essentially changes the sign everywhere in numerator and the denominator. So those are both perfectly valid. Now, that is Calculus 1. This is how we did this problem in Calculus 1. I know because I teach it in Calculus 1. But now we want to learn a different way, perhaps an easier way, using what we know from Calculus 3. Okay, so let's think about the left-hand side of that equation as a function. So it was a function f that was based on x and y. So you have some function f that's based on two variables, x and y. X, of course, depends on x, so that's pretty easy. Y was some function of x, right? So y is a function of x. Right? That's why there's this variable right here. Okay, so now how in the world does that help us? Well, because then if I want that derivative of f with respect to x, then I would say, well, let's go down this side. I would take the partial derivative of f with respect to x, and then, of course, dx dx, which, of course, disappears. We just saw that on the previous page. Dx over dx is 1. It's the kind of thing that's so trivial we don't usually spend a lot of time with it. Right? Then what about the other side? Well, that would be the partial derivative of f with respect to y times dy dx. And of course, if the whole thing's equal to 0, then it just equals 0 because the derivative of 0 is 0, so that's pretty easy. Well, how did this help us? Well, let's see. If I'm trying to find dy dx, I mean, if that's my goal, if this is what I'm looking for like it was on the previous page, then couldn't I subtract this piece over to the other side and say, hey, the partial derivative of f with respect to y, dy dx, that's what I'm looking for, equals the negative, because I'm going to subtract this, negative partial derivative of f with respect to x. And therefore, dy dx, this is a formula. You can put a box around it and highlight it and everything. Dy dx is equal to the negative partial derivative of f with respect to x divided by the partial derivative of f with respect to y. That gets us out of all sorts of work. And it's way easier to use than the previous formula, right? So dy dx is this. Now let me show you why it's easier. Let's do it. Okay, so we have this function right here that we just did. So we just did this in a calculus 1 way. According to my formula, if I want dy dx, I want the negative partial derivative of f with respect to x over the partial derivative of f with respect to y, keeping in mind that this function right here is f of x comma y. Okay, so that would be negative, and then we take the partial derivative of this with respect to x, which we know how to do in our head. So that's 3x squared plus the derivative of this with respect to x, right? So x is your only variable, so that would be 3 times y squared, because y squared is treated like a constant, and derivative of a constant is 0, so there's nothing there. So minus 0 for the back one. And no, you don't even have to show the minus 0 part if you don't want to. I just want you to understand where it comes from. All right, now I take the derivative of it with respect to y. So derivative of this with respect to y is 0. If y is your only variable, you bring the 2 down. 3 times 2 is 6, so 3x times 2y, if you will. And then minus 5y to the 4th. And if you're thinking, that looks familiar, yes, it's because it's what we had on the previous page. So it's negative 3x squared minus 3y squared over 6xy minus 5y to the 4th. We found the same answer as the Calc 1 method, but with a lot less work. Which shows us that this chain rule has a great application, something that will make things go a lot easier for us. When we're trying to find dy dx, we can use this method instead for a function that's defined in terms of x and y.